Okay, we've got the classroom. I think there's a couple of others that will be joining us shortly. Okay, hopefully the two watching from home will join here shortly. So we have this system, the really distinction is the fact that we're tweaking this frequency source, what we maybe called local oscillator in the past. Now it's a synthesizer, and we can program this very quickly, right? So you need something that can switch frequencies pretty quickly. So there's some engineering challenges there. We've got that solved these days, but and then you're having this deterministic but noise-like generator. Okay, so we have one more home viewer connected, and there was someone else watching, but hopefully they'll catch up soon and connect. So, all right, so this is an example of a frequency hopping pattern. So you along the bottom you have these time slots, and along the vertical axis here we have the different frequency channels. So these would represent different chunks of frequency that we are stepping to, right? So in this case, in the first time instance, we're going to transmit here, and then here, and down here, and so on, right? So for a slow hopping signal, we would transmit multiple symbols, or FSK symbols, during a particular time slot. We call these time slots chips. So we'll have a chip period or a chipping rate. So during a chip in a slow hopping situation, you might have one or more symbols transmitted during this hop. And then we'd hop to another frequency, and then we'll have some more transmitted. In an FSK system, you might have some deviation here that represents one frequency might be one symbol, another frequency would represent another symbol. That could be within this slot if these slots are pretty coarse, or it could actually be just multiple slots. But most likely you're going to be doing it within this so that we can have other type of sequences, hopping patterns that would be orthogonal to this one, right? And so fast hopping, you would transmit a single symbol, might take several of these hops, right? And so you would need to step your synthesizer to these different frequencies, measure that information, energy content in the different ways that we demodulate an FSK symbol, and then add all these up, right? So let's look at this. Didn't put a slide title on this one, but for a symbol period, we'll call that TS.
Professor?
FSK symbol is, so this.
Hello.
Doctor?
Yeah,
I just had a question about the previous slide.
sure.
You were saying one symbol can take several time hops. So is it parts of one symbol, like on each hop, or is it the same symbol repeated a couple of times?
Yeah, so basically you would take a single symbol, and then you would hop within that symbol. And yeah, there's some subtleties on how do you achieve synchronization. This is why FSK is a little bit easier, because with quadrature amplitude demodulation, we need to do that with what's called coherently. We haven't gone into the mechanics of that. That's that symbol synchronization, process carrier synchronization, and timing recovery. That's more of an advanced topic, and in fact, I kind of put that on the extra credit as an option to look at. The but the idea of FSK is that it's a little bit more forgiving on that type of demodulation, but you would be switching the frequencies here in these frequency synthesizers multiple times throughout a single symbol in the fast hopping case, right? And so, but you're still like looking at the energy in one of those deviations of the symbols, right? So in FSK, remember that we map, let's say in a binary FSK system, we're sending a bit 0 and a bit 1, and each of those corresponds to a different frequency deviation from the mean frequency, right? So you're aggregating or summing up the energy in those frequency bends during that whole symbol time period, regardless of where we're hopping. Okay, so I hope that answers the question. To really answer it, we would want to go into all the mechanics of how that's done, and we simply don't have the time for that. But okay.
Thank you.
All right, so we've got this symbol or signal of the FSK, where this is just A cosine omega mt and Vm. So if it's phase modulation, we can mess with the phi for frequency. FSK, we're messing with the omega, right? And so that T is varying throughout a particular symbol time, right? And this omega m, well, that depends on if we're binary or 4 or 8 or 16 or that type of thing, right? So we would have different frequencies that this omega can take on, right? So this might be plus or minus 1/2 delta W about a average center frequency, right? WC is omega C is our average center frequency. But if M is larger than 2, then we could have more factors here, right? So during each chip period, T sub C, right, the synthesizer output is now going to have this hopping term added to it, right? And so this hopping omega is going to be some function that is known to both the transmitter and the receiver that varies over this chip period T sub C. Okay, so where these chips are each slot that we're hopping on, right? Now, if T sub C, if that time period of the chip is less than a time period of a symbol, then we call that fast hopping, and typically it's much less, right? So we're hopping many times throughout a symbol period. Conversely, if the symbol period is less than the chip period or equal to, then we call it slow hopping, right? So fast hopping, as we'll see, has some advantages, but it's a much more complex and expensive system to use. So let's look at the performance with a jammer. We'll look at 3 different cases here. This is just the idea that we're going to use a broadband jammer and compare it to the non-hopping case, right? So here, if our bandwidth of our basic signal is B FSK, right? So that's going to be closely related to the frequency separation between the FSK symbols, right? And then we talk about spread spectrum as using an excess of that necessary bandwidth. So we'll look at that as a factor of L, and L is called our spreading factor, and that's typically an integer. And so our bandwidth of our frequency hopping spread spectrum system is now L times that fundamental basic bandwidth. Okay, now let's assume we have a jammer J producing some interference I. Let's look at the energy per bit divided by the interference, right? So up till now, we've looked at the energy per bit over the noise, the EBNO, or the signal to noise ratio, depending upon whether we're looking at the bit level or a symbol signal level, right? So, but now instead of looking at AWGN noise, we're going to look at that as an interference. Both noise and interference can cause bit error rates, right? They can confuse that receiver. So now that's at total energy, right? But let's look at the power spectral density over a certain bandwidth, right? So we're just kind of substituting in this power of the jamming signal divided by the bandwidth of that thing, right? And of the symbol, right? In this case, we're not using spread spectrum, so that jammer is then trying to cover the bandwidth of the signal, right? So now we just rearrange terms, and we've got this EB divided by the power of the jammer times the bandwidth of the symbol. Now let's consider spread spectrum and try to make our jammer broadband. So instead of just being a narrowband jammer, we're going to make it cover the whole band over which this system is spread and frequency hopping. So we start with the same concept, but now here the difference is that we're dividing by this chipped bandwidth. Okay, the bandwidth of the system after it's been chipped or spread, right? So so we know that this bandwidth is actually larger than the FSK by this factor of L. So our by forcing the jammer that has this finite amount of power, that's kind of an implicit assumption, is that it costs a certain amount to build and operate a jammer at a certain power, and if we try to spread that over a larger bandwidth, then its effect is going to be diminished by this factor of L. So our signal to interference ratio is improved by this factor of L by operating our signal over a wider bandwidth and forcing a crude, unintelligent jammer to spread its energy over that wider bandwidth. This is, assuming also that your jammer is not smart enough to try to follow you around as you hop, right? So that can be done, but it's a much more sophisticated jammer and stuff. So so we see already there's an improvement there, right? Now let's look at partial band jamming. Now our jammer is only jamming over a narrow bandwidth, and it is able to concentrate all its power in a particular channel, right? And but it's so powerful, we're going to make this assumption that it's essentially able to destroy the signal to the point where our bit error rate is 0.5. It's essentially equivalent to a coin toss. Once you've done that, then you'll have no idea of whether it's a 0 or a 1, right? That was transmitted. They're equal probable. So that would be great for the jammer and bad for the person or the entity trying to communicate, right? Let's also look at slow hopping. So in this case, we'll assume that our chip rate is the same as our symbol rate. So there's one symbol per slot or per hop per chip. Okay. And we could, still be slow hopping and sending multiple symbols, but we're gonna per chip, but we're gonna assume that these are equal in this case. Now, probably a bit error then is we're going to say that when we land on this, I'm sorry, I keep using my wrong screen. When we land on, when we hop onto the same channel, same frequency bin that the jammer's at, we're going to have a probability of error of 1/2. Okay, that coin toss, right? So, but that's only going to happen 1/L times, right? And all the other times, we're basically going to get the bit error rate that we would with a binary FSK system. Okay, we'll assume it's binary here. And so that's E 1/2 e to the minus energy per bit divided by 2 times the noise power spectral density, right? But that is going to occur L minus 1 over L times, right? So most of the time, especially if L is large, we're getting the regular FSK performance, and the other times we're getting this terrible performance. So that's going to be greater than or equal to this 1/2L, right? So by that amount, right? So that's the idea. So even though that jammer is able to destroy our communications during one slot, we're able to communicate effectively during all the other slots. So if we use some error control coding, block codes, convolutional codes, then we can do some forward error correcting and even deal with that type of thing there. So now let's consider a fast hopping system where the chip period is much less than the symbol period, where the chipping rate is much faster than the symbol rate, right? So and so now each symbol is sent over some subset of the L bands, right? So if we have the spreading factor L, that is representing there's that many different bands that we can hop to. But during a symbol, when we're hopping, we're going to hop over up to a subset up to L bands, right? So our L hopping is less than or equal to L, right? So and that's really this the symbol time divided by the chip time, right? How long do we stay at any particular frequency relative to the length of a single symbol, right? So now that means that a symbol will encounter partial jamming with this probability of LH over L, right? So we can approximate a binary FSK signal's performance by assuming that its energy is wasted or discarded when jammed. So what does that look like? That looks like this type of relationship here, where we're going to scale its energy by this relationship, right? So its energy per bit now is scaled by LH minus 1 over LH. So then we can plug this in and look at this bit error rate here and this bit error rate there, and then we can rearrange some terms. And here the trying to figure out what time it is here. Okay, if L is much greater than 1, okay, that now we're spreading over a large band, right? Then the fast hopping frequency hopping spectrum has a superior bit error rate. So we kind of go from here to here, and note that this term up here, this TS minus TC divided by TS, that's approximately 1 if TC is very small compared to TS, right? So this is approximately equal to 1, so we'll substitute that in there. And then we'll notice that these terms have the same base and exponent associated with it, so we can just add them together. And so this TS over LTCs, these cancel out, and we end up with this, which is essentially the bit error rate for a binary FSK system, right? So by using fast hopping and over a large number of hops, then we've made it essentially immune to narrowband jamming. And so the fast hopping frequency fast frequency hopping spread spectrum is able to approach total immunity to a narrowband static jammer. Okay, and that's why it's used in these high-end military systems. It's more expensive to be able to switch that fast within a symbol rate, right? So if you're trying to send data at a certain rate, that determines your symbol rate. Based upon how many M-ARY are you doing, binary versus higher order modulation. But if you're trying to send data at a certain rate, if we can spread that over a broader area, we can achieve this anti-jam capability. But we're having to create an expensive frequency synthesizer system to be able to step that fast, right? So non-trivial, but definitely has its advantages. All right, so now we're going to look at direct sequence, and we have time to finish here. So direct sequence is another very common system, maybe in some ways even more common than frequency hopping. But now we're going to exclusive OR a symbol waveform with a pseudo-random sequence. Here it's going to be basically zeros and ones. So a pseudo-random sequence of bits. Depending on how you implement it, it might be -1 and 1 or 0 and 1. But it's typically a binary type of sequence, but it's at a much higher chip rate, right? So the sequence, the data or symbol sequence coming in is at one rate, and then we're chipping it at a much higher rate. Okay, and typically the way that's going to work is you're going to invert your bits when you have a -1, and when it's a 1, it stays the same. So you're going to take a single symbol and you're going to kind of chop it up, and in some of those chip periods, it's going to be the same, and in other cases, it's going to be inverted, right, according to a specific pattern. So because that now our rate of this chipped version is much higher, that requires more bandwidth to send. So we're spreading that signal over a broader bandwidth. The distinction between the frequency hopping system is that frequency hopping tends to occupy any given instant, it's occupying a narrow bandwidth, but over time, it's visiting all sorts of different channels throughout that spectrum. And so its overall bandwidth is very large, but at any given instant in time, it's narrow. In this case, in the direct sequence case, we're spreading it simultaneously. So our power spectral density, we looked at this, is broader and covering the whole spectral range. The signal can be recovered at the receiver by XORing it again with the chipping sequence. And so if we, pseudo randomly flip the sign of the input symbol, if we kind of replicate that process at the receiver, then we can recover that original symbol. Okay? And again, we might use orthogonal chipping sequences so that multiple users can share that spectrum. I guess I didn't finish that sentence, did I? Can share the same spectrum. We can support multiple users. When we do that, now we're talking code division multiple access, or CDMA. I'm sure you've heard of CDMA because that's dominant in the previous generations of cell phones standards, at least in the US. In Europe and much of the rest of the world, they did not use CDMA, but like US and South Korea and maybe a few others use CDMA in both 2G and 3 and 3.5G type communication cell systems. So this is what it looks like. So I tried to draw this similar to the frequency hopping system. And here, though, instead of necessarily shifting the signal to different discrete frequencies, we're chipping it with a pseudo noise code generator that goes through this chip pulse generator. So this is going to be a code. This is going to map that code to maybe plus ones and minus ones. And then we're going to multiply that symbol or signal of symbols coming in from the, let's say, a Comm modulator here, right? And in this case, the rate of our chipping signal is much higher, and therefore the spread signal has a much wider bandwidth after it's been multiplied. We synchronize this over to the receiver, and so we get it timed right. We're using the same sequence starting at the same time. It's non-trivial to do, but that's an implementation issue. And we then chip this result, and now we can recover that original symbol and then pump it back into our Comm detector. So again, this top channel is kind of the basic non-spread version, but we're chipping it at a much higher rate to spread it. Okay, so an example, we often use linear feedback shift registers to accomplish this. So this would show you some sort of code. You start maybe with all zeros, and you put a 1 into here, and you start moving that down. You may peel off the last bit and the first bit, modulo 2, add those together and stick that in your input again. That's going to generate this pseudo random code, and then we're going to pull this as an output, right? This is, again, pseudo noise-like, pseudo random, but it is deterministic. If you know these taps and the length of this, then you can replicate that at the receiver. Okay. And all right, so what we want is we want a long periodicity before these codes repeat. Okay. And we want noise-like autocorrelation. What does that mean? Well, if we remember our AWGN, additive white Gaussian noise, in the ideal case, it has a power spectral density that's flat from DC to infinity, right? And but its autocorrelation is an impulse, right? At an offset as tau is equal to 0. It's an impulse, and so you have perfect correlation when things align, and 0 correlation everywhere else, right? That's what we want, because we want that receiver to be able to perfectly reconstruct the original signal. That's what we're kind of doing, is that autocorrelation process. So we want to be able to exactly replicate the original signal, and but if we want to be able to support multiple users in the same band, we want a very low cross correlation. So we want that chipping sequence to have a almost 0 correlation with any other chipping sequences that we would be using. All right, so some examples: Gen 2 and Gen 3 cell phone systems, especially in the USA. You might have heard WCDMA. That's a wideband CDMA. It's chipping over a broader bandwidth. I think that was like 3.5 megahertz or something like that. Link 16 that I mentioned earlier is actually a hybrid of DSS, direct sequence, and frequency hopping systems. GPS or GLONASS or Galileo, or these are different global navigation satellite systems, GNSS. GPS is one example of that, but they all use some form of direct sequence spread spectrum. And the interesting thing is that allows you to have multiple satellites transmitting its timing signal at the same frequency, but the receiver can distinguish them very easily, right? Using these pseudo-random codes. And so I need to do that because to get a good position fix with altitude, I need 3 or 4 satellites, right? 4 satellites to be able to trilaterate and be able to compare times at which those signals arrive with the location, the known location of those satellites. They're circling in a very well-known predictable orbit. So I measure the time at which I'm getting these different pseudo-random codes, and I'm able to look at one frequency band and extract out these different ones because they're using orthogonal codes. And I despread them and then compare the times. And I can do some mathematical calculations and figure out what where I'm at and what time it is, right? So our early Wi-Fi standards used direct hopping, direct sequence spread spectrum, 802.11b. The newer ones use orthogonal frequency division multiplexing, which is what 4G and 5G cell phone systems use. And we'll talk about that in another few lectures next week or the week after. Semester is almost over, so we're trying to cover a lot of ground now. Trying to give you some good information, but maybe at a little higher level. All right, to wrap up then, let's look at Chirp spread spectrum. Here you can see in this diagram down here, you might have a waveform that varies in frequency over time. At the beginning of this, it's a low frequency, low periodicity. At the end of this sorry, I keep pointing to the wrong screen with my cursor. So over here at the early time, we've got low frequency, we've got high frequency over here, right? So this is a linear chirp. It's if you drew the frequency versus time, it would be a straight line with an upslope to it, right? And so you take your signal coming in and you multiply it by this chirp, and now your output or your composite signal that you transmit will be constantly changing frequency throughout the time duration of this chirp. And then generally it's set back down to the low frequency and repeated. So it kind of looks like a sawtooth in the frequency domain, right? Frequency versus time plot. At the receiver, you would multiply it by the opposite slope chirp when it goes down, and then be able to recover it. So so we just use the opposite slope. Very, very common in radar. Don't see it as often, near as often in communications. But low raw is a very low data rate, but medium distance communication system. It can work over several miles, and it uses chirp spread spectrum. Okay, so that's it for today. Remember, pass the word. The exam has been changed from Friday until a week from today, Tuesday. You're welcome. And be getting in any extra credit. Let me know if you need more time. I will work with you on that. And labs and homework assignment. Expect the test to be just like homework 3 and 4. And I will ask a conceptual question on spectrum. I'm not going to ask you to do any of that, all those equations we did there, because we don't have time to do a homework assignment on that. But I will ask you some conceptual questions on that. Okay. Anything else?
No, I think they're good. Have a good, Professor.
All right. Take care. See you on Friday.
Yeah.